All right, today we're going to go on a pretty incredible journey. It's the journey of light itself, starting from the mind-boggling distances of space, cutting right through our atmosphere, and finally landing inside the amazing biological camera that lets us see it all, the human eye. We're going to tackle some of those simple questions that actually lead to some really profound answers about our world.
You know, it's one of the first big questions we all ask as kids, right? And it's a brilliant one. It seems so simple, but the answer takes us straight to the heart of how light and matter actually work together. And hey, here's another classic. You look up at the night sky and you see the stars flickering, twinkling beautifully, but then you see Jupiter or Venus, and they just shine with this steady, constant light. So what's the difference? Well, the secret to both of these cosmic mysteries isn't actually out in space. It's right here in the air all around us. Yep, that's right. The answers to both of these riddles are found right here in our own wondrous, colorful sky. That thin blanket of gas we call the atmosphere, it's responsible for some of the most beautiful things we get to see. It all comes down to a principle called atmospheric refraction. Now, that's just a technical way of saying the bending of light. You see, you have to think of our atmosphere not as one single thing, but as a bunch of different layers of air, all with different temperatures and densities. Each layer bends light just a little bit differently. So as starlight travels through all these shifting, swirling layers, its path gets wobbly. And that constant bending is the secret behind the twinkle. Now here's where it gets really interesting. Because stars are so unbelievably far away, all their light reaches us as a single tiny point. And that tiny little beam of light gets knocked around really easily by the turbulence in the air, which makes it look like it's flickering. But planets, they're much closer to us. So they don't look like a point, they look like a tiny disk. Even if some rays of light from the planet are getting bent one way, others are getting bent another way, and it all just averages out to a nice, steady glow. Simple as that. So what about that blue sky? Well, that's a different effect called scattering. Sunlight, as you know, is made up of a whole rainbow of colors. When that sunlight hits the tiny molecules in our atmosphere, the blue light, which has a shorter wavelength, gets scattered all over the place, way more than the red light does. Our eyes just pick up all that scattered blue light coming from every direction, and voila, the sky looks blue. Okay, so scattering explains the sky's color, but what happens when that same sunlight hits, say, a water droplet? Well, then we get another spectacular effect, the rainbow. And this is all about splitting light apart. You've probably seen this happen with a glass prism, right? White light goes in one side, and out comes this beautiful band of colors. That process is called dispersion, and it reveals a pretty fundamental secret. White light isn't really white at all. It's actually a mix of all the colors of the rainbow, which we can remember with that handy acronym, VIBGYOR. A rainbow is basically what happens when you have millions of tiny little prisms floating in the sky. As sunlight enters a raindrop, it bends and splits into its different colors. Then, that light bounces off the back of the raindrop, and as it comes back out, it bends again. This whole process separates the colors perfectly, creating that beautiful arc we all love to see. Okay. So we've talked about light bending, scattering, splitting, all this amazing physics happening in the world around us. But honestly, none of that would matter if we didn't have a way to detect it. So how does all this information, all this light and color, get turned into a picture inside our heads? Well, for that, we need to look inward. The answer, of course, lies in one of the most incredible organs in the entire natural world, the human eye. And to understand how it works, the best way to think about it is like a camera, a really advanced one. It's a great analogy. Just like a camera focuses light onto a digital sensor or a piece of film to create a picture, your eye focuses light onto a light-sensitive screen at the very back called the retina. And the retina, well, that's where the real magic of sight begins.
So let's quickly build our biological camera. First, light hits the cornea, that clear outer layer, which does most of the heavy lifting when it comes to bending the light. Next, you have the iris, that's the colored part of your eye, which controls the size of your pupil to let more or less light in, just like a camera's aperture. Then the lens does the fine-tuning, making small adjustments to get the focus perfectly sharp on the retina. And finally, the retina itself, this delicate membrane packed with cells that turn light into the electrical signals our brain can actually understand as an image. And one of the most amazing features of the eye is its autofocus. It's called the power of accommodation. Just think about it for a second. Right now, tiny muscles in your eye are constantly changing the shape of your lens, letting you shift focus from something far away to the words on this screen in an instant. It's this incredible, seamless process that you don't even have to think about. But of course, sometimes this natural camera doesn't focus light perfectly onto the retina. We call these refractive errors, and they are super common. Let's take a quick look at the two most frequent types.
First up, we've got myopia, which most people know as nearsightedness. If you have myopia, you can read a book or look at your phone just fine, but things far away, like a road sign down the street, just look blurry.
So what's actually going on here? Well, in a myopic eye, the eyeball might be a little too long, or the cornea might be a bit too curved. And what that does is cause the light from distant objects to come into focus in front of the retina, not on it. So by the time the light rays actually hit the retina, they've already started to spread out again, and that creates a blurry image.
The fix, though, is pretty elegant. You just place a concave lens, in glasses or contacts, in front of the eye. This lens spreads the light rays out just a tiny bit before they enter the eye, which has the effect of pushing the focal point backward, right onto the retina where it's supposed to be.
Now, the opposite problem is hypermetropia, or farsightedness. With this, distant objects are usually clear, but trying to focus on something up close is really difficult and can cause a lot of eye strain. In this case, the eyeball might be a little too short, or the lens just isn't powerful enough. What this means is the eye's focusing system can't bend the light from nearby objects sharply enough to get them in focus. It tries to form an image, but the ideal focal point ends up landing behind the retina, which again results in a blurry image on its surface.
And the solution here is the opposite kind of lens, a convex lens. This lens helps converge the light rays, giving the eye that little extra focusing boost it needs to pull the image forward and land it perfectly on the retina.
So we've gone from the physics of the sky to the biology of the eye. But you know, understanding the science behind vision also gives you this profound appreciation for what an incredible gift it is. A gift that, sadly, not everyone has, but one that can sometimes be shared.
Take a look at this number, 4.5 million. That's how many people with what's called corneal blindness can actually be cured. Their sight can be restored through the simple yet profound act of eye donation. It's a powerful reminder that our eyes can give someone the gift of sight long after we're gone.
And I want to leave you with this quote. It's a really humbling reflection on what it means to actually see the world. From the twinkle of a distant star to the colors of a rainbow, vision quite literally paints our reality. It's a wonder of both physics and biology, and truly an incredible gift to be cherished.